All right, hello everyone. In section 4.5, we're going to be looking at indeterminate forms and something known as L'Hôpital's rule. So this is going to feel a little bit different than the last few sections because it is going to be a different application that's not as much focused on optimization, but it's how we can actually use the derivative. So we spent 11 sections in chapter 3. We want to use the derivative to help us back with chapter 2. So that'll be to find limits. So we can actually use the derivative to find limits. And yes, the derivative is the limit of the difference quotient, but we can now use our derivative rules to go ahead and consider derivatives or limits that we couldn't find before. So the limit returns. It sounds like a bad sweet sequel, but it won't be too bad. Discuss the behavior of this given function, x minus sine of x over x cubed near x equals 0. So remember, whenever you're discussing about something near a certain x value, you're really just considering the limit. And remember, the first thing that you should do when you go to compute a limit is just try to plug it in. So if you plug this in, you get 0 minus sine of 0 over 0 cubed, which of course is 0 over 0 because sine of 0 is 0. So if you remember, this was the scenario where we would have to factor and cancel. But obviously we can't factor and cancel this, so that doesn't work. So before we used to consider a few things like maybe we would try to go ahead and use the sandwich theorem, which again requires quite a bit of setup and picking the right functions that sandwich that. So that's not the easiest thing to do. Another thing that we could go ahead and do is just look at the graph. And again, this requires a lot of, to get a very precise graph, it requires some sort of tool, and we're kind of taking the approach of like, okay, imagine we were trying to develop calculus and learn how it developed without necessarily the technology we have today. So if we look at the graph where we have a very precise graph right here, you can see that we do have approximately 0.167 or 66 as the limit. But again, that relied on us being able to get a very precise graph right here, even down to thousandths place. So again, at this current stage, we have some limitations on finding the limits. No pun intended there, actually. But one other technique that we could use, and we're going to introduce right now, is, as stated above, L'Hôpital's rule, or just Hôpital, so French mathematician. And essentially, I'm going to go ahead and just illustrate the rule. And it does have this one thing where I need to check. We're going to need to make sure we have something like 0 over 0 or some other indeterminate form. And we'll look at other types of indeterminate forms as we go through the examples. But let's just go ahead and see how L'Hôpital's rule works. And the reason it works is because we have a limit that's in indeterminate form. 0 over 0, again, is indeterminate. So what we're going to do with L'Hôpital's rule is we're going to consider the numerator and the denominator separately. So let's go ahead and consider the numerator of this function and take the derivative of that. The derivative of x minus sine of x is going to be equal to 1 minus cosine of x. So I'm going to just write it down here so we have it for reference. The limit as x goes to 0 of x minus sine of x divided by x cubed. I'm going to treat the numerator and the denominator separately. So I'm going to take the limit of I'm going to take the derivative of the numerator. And I'm also going to take the derivative of the denominator. The derivative of the denominator is 3x squared. So what L'Hôpital's rule says is that these two functions have the same limit. So what we could, and again, the intuition here, again, the formal proof is a little bit tedious, but the intuition here is if you're looking at the ratio of the original function, it is going to be the same if you look at the ratio of the derivatives, because again, the derivatives are made by considering the limit of the difference quotient. So these two actually have the same limit. So what I'm going to now do is I'm going to go ahead and see if I could plug in 0 here. So we have 1 minus cosine of 0 divided by 3 times 0 squared, which is 1 minus 1 over 0, which is again 0 over 0. But notice 0 over 0 is another indeterminate form. So this is not our answer, so maybe I shouldn't use the check, but this is indeterminate. Whenever you have an indeterminate form, you can go ahead and take the derivative of the numerator and the denominator separately. So do not use the quotient rule, and realize that the limit of the quotient of the derivatives will have the same limit. So let's take the derivative of the top and bottom again. What is the derivative of 1 minus cosine? Well, let me go ahead and just illustrate. I'm going to take the derivative of the top. This will just be sine of x. And now let's take the derivative of the denominator. Let's take the derivative of this, and we see that we have 6x. All right, guess what? Let's try and plug in 0. Sine of 0 over 6 times 0 is equal to 0 over 0. Again, that's indeterminate. So what I'm going to do what I'm going to do again is, you guessed it, take the derivative of the top and bottom separately. So we have the limit as x goes to 0. Taking the derivative of sine of x, you have cosine of x. Taking the derivative of 6x, you have 6. And now take the limit of this function right here. You get cosine of 0 over 6, which is 1/6. This is an actual number. It is the limit. So that's how the Hôpital rule works. And we're really just going to spend the rest of the day looking at different scenarios of how to use this rule. So again, the important thing to note about Hôpital's rule is that it does require us to check that we have an indeterminate form. An indeterminate form is a meaningless expression that we cannot evaluate. So this is the definition of an indeterminate form. That sounds like quite the insult, to be honest. Like, you are a meaningless expression. I'm like, I'm sorry. Just take the derivative and I'll mean something. Anyway, 0 over 0, of course, is one of the appearances of it. And we also have things like whenever you consider like an infinity over infinity, that's another thing that means nothing. But you could go ahead and use this rule with. We'll also look at infinity times 0 or infinity minus infinity. And again, these show up whenever you're considering limits. So a summary of what we did in that first problem is given in the rule right here and the steps down here. And I do have one important thing I do need to make sure we're careful of, and I'll kind of do an example of how you could get something wrong if you're not careful with that. But what this is saying, let's focus on this. This is, let's take the limit of some quotient or some fraction where you have a function on the top and bottom. The limit of that is the same as the limit of the derivative of the numerator divided by the derivative of the denominator. So the steps determine that the limit is in an indeterminate form. Indeterminate form. Then take the derivative of the numerator and take the derivative of the denominator. But again, I'm really trying to emphasize you do not use the quotient rule. Do not use the quotient rule. you're not taking the derivative of the function, you're taking the limit, which requires us to take the derivative of the top and the derivative of the bottom separately and look at them as a ratio. And then what we did in the first example is you simply repeat steps 1 and 2 as long as you get an indeterminate form. You can technically do it forever, but hopefully, and we'll see these few examples, it's going to reduce to something that you could actually consider the limit of. So 4, once you get a real value, stop. That value is your limit. Because the temptation may be to just keep going, but again, you can only use this idea when you have an indeterminate form. So once you have some real value, like we had 1, 6 up here, stop. And again, it may be worth noting that this procedure also works for one-sided limits. So let's go ahead and just do a few more and make sure we're comfortable with the different scenarios and especially the other indeterminate forms we may run into. And it's not stated here, this also works for infinite limits. So, and for infinite limits. So if x was approaching infinity. So on the next page, we have a few more examples. This first one is very similar to the one we did on the first page. So I'm going to go ahead and illustrate it, and it won't be as many steps, but remember, step 1, try to take the limit. 3 times 0 minus sine of 0 over 0 is 0 over 0. So we have an indeterminate form. So now let's apply L'Hopital's rule. So taking the derivative of the top, I get 3 minus cosine of 0. No, excuse me, cosine of x. I'm not plugging in 0 here yet. Divided by 1. So now let's try to take the limit as x approaches 0. And we get 3 minus cosine of 0 divided by 1, which is 3 minus 1 over 1, which is 2. Stop. We have some real value. We know that the limit indeed is 2 using L'Hopital's rule. So go ahead and pause the video and see if you could figure out the limit here using L'Hopital's rule. So here's the solution to the one on the right. So again, before we could use L'Hopital's rule, always check that it's in determinate form. So 7 times 6 minus 42 divided by 7 times 6 squared minus 252. Well, this is going to be 42 minus 42 divided by, let's see, 7 times 36 minus 252, which is going to give you 0 over 0 once you do the multiplication there to verify that. But 0 over 0, let's now use L'Hopital's rule, which means the limit of the original function is going to be the same as the limit of the derivatives of the numerator and denominator's derivative taken separately. So this is just going to be 7 minus 0 divided by 14 x minus 200, and wait, that goes to 0. So of course, again, you really didn't need to put the zeros if you were okay with the derivative of a constant, which hopefully you are okay with that by this point. But now what we're going to go ahead and do, I would even suggest before you plug in the 6 to maybe just simplify this as the limit as x approaches 6 of 1 over 2x. That just is a little easier to cancel now than later, which of course now you can go ahead and plug in 6 and get 1 over 2 times 6, and we find the limit is 1/12. So again, just make sure you're checking indeterminate forms, and this one illustrates, remember that you can always still simplify as you go through. So like for example, if you have 0 over 0 again here, I would definitely still try to simplify at each step. And before we move on to maybe some more complicated ones, let me again just emphasize. First, we are not using the quotient rule. We're taking the derivative of the top and the bottom separately. And the second thing to really make sure you don't get carried away, I know this rule is very exciting, but whenever you see a real number, make sure you stop. Don't keep taking the derivatives. It's as much fun as you're having. Just see like, okay, take it and continue as long as you have an indeterminate form. And just to illustrate what would happen if you and you got to be careful. Like, let me show you what happens here. Let's again plug in 0 because we're asked to take the limit. This is 1 minus cosine of 0 divided by 0 plus 0 squared, which is 0 over 0. And then we'll take the derivative. So this will be equal to the limit as x approaches 0 of sine of x, because the derivative of cosine is minus sine, over 1 minus 2x. So plug in 0 again, try to take the limit. So you get sine of 0 over 1 minus 2 times 0, which is 0 over 1. And this is, again, you got the 0 in the numerator, but that's okay. Remember, 0 in the numerator is 0 divided by anything is 0. It's whenever you have the 0 over 0 is whenever you can use L'Hôpital's rule. So make sure you stop here. That's your answer. And just to illustrate what would happen if you didn't stop, you would again maybe be like the limit as x approaches 0, and you would have cosine of x over 2, which would give you 1/2. But notice that this is different. So make sure that you actually stop once you find the some real value. You can only use L'Hôpital's rule when you have an indeterminate form. So this do not do, because we did not have an indeterminate form. With that being said, let's go ahead and just kind of illustrate a few other scenarios where this is useful. So on the next page, we have these two functions right here. And again, you could technically use our previous techniques. This one would get a little bit nasty because remember, if you're looking at the square root, in order to take, well, first of all, take a quick moment and see if it's indeterminate, because it may be one of those things you plug it in and you get some real value. No L'Hôpital's rule, no factoring or canceling necessary. So let's plug in 0. We get 1 plus 0 minus 1 minus 0 over 2 divided by 0 squared. Quick little check, these two cancel. This goes to 0 and that's 0. So indeed, this is 0 over 0. And sometimes it is a little bit overwhelming to look at this all at once. So do what you need to do to make sure that you do the calculus correct. So you may just want to like even just rewrite this as like 1 plus x to the 1/2 minus 1 minus x over 2 off to the side, just to kind of think, okay, how do I take the derivative of that? Well, take the derivative of the numerator. You're going to get, hopefully you're okay with the 1/2. We've dealt with the square root quite a bit. So this would end up just coming out to 1/2 1 plus x to the negative 1/2. The 0, the derivative of the constant is 0. And again, don't let this throw you. You don't need the quotient rule or anything here. Just remember that this is actually the same thing as 1/2 times x. So the derivative of 1/2 times x is just 1/2. So the derivative of our whole numerator is just going to be 1 over 2 square root of 1 plus x after I clean up what happens with this. And we would have minus 1/2. And then the derivative of the denominator separately is just 2x. So again, this one actually is a little bit, I don't know, overwhelming to look at, but that's why you still need to just kind of remember, how can I clean this up? And you may not even want to clean it up yet. You may just want to be like, oh, what if I plug in 0? Even just a quick glance through, I'll see that you'll get 1/2 minus 1/2 over 0. So again, we don't have our limit. But before we take the derivative again, I'm going to go ahead and clean this up just a little bit. So there's a couple ways you could approach this problem of cleaning up. The one thing you can go ahead and do is just, you could go ahead and factor out the 1/2, or actually the way I'm going to think about this, no, I'll factor out the 1/2. So we have the limit as x goes to 0. I'm going to factor out the 1/2, which gives me 1 over 1, let's see, the square root of 1 plus x minus 1 divided by 2x. So again, just kind of thinking how I could simplify this. All right. Yeah, we could do it like this. And is there a better way? This will work. So I'm just trying to decide what way I want to do this. Yeah, we could do this. So you could go ahead and consider the limit as x approaches 0. And remember, you're just going to be, you're thinking about this compound fraction is quite a bit to look at. So you're like, okay, I'm dividing by 2x. So this would be the same thing as multiplying by the reciprocal, 2x over 1. So you could actually think about this as 1 over 2 times 1 over the square root of 1 plus x minus 1. Multiplying by the reciprocal is 1 over 2x. And then you can distribute this, and you would have, you know what? I wouldn't do it this way. So let me back this up. Actually, what I would do here, this is just, there's too much fraction work here. So let's back this up. A better approach would be actually to rewrite this in terms of powers. So let's try that. Let's do it this way instead. As x approaches 0, and the 1/2 could actually come out into the front, and I'm going to rewrite my numerator as 1 plus x to the negative 1/2 minus 1, and then we have 2x in the denominator. You could even put this 1/2 all the way out in front of the limit if you want. I'm just going to leave it there though. So again, we verified that this was an indeterminate form right up here. So now we can go ahead and just take the derivative of this again. So we have the limit as x approaches 0 of 1/2 times this negative 1/2 comes down. You have 1 plus x to the negative 3/2, and all of this divided by 2. And now, again, you can clean up a little bit first if you want, but you can also just plug in 0 here and see what happens. So you get 1/2 times negative 1/2. You get 1/2 times negative 1/2. And then this will be 1 plus 0 to the negative 3/2 all over 2. And this will be negative 1/4 times 1 divided by 2. And then negative 1/4 divided by 2. Again, you could think about this as multiplying by the reciprocal. It's negative 1/4 times 1/2, which gives you negative 1/8. There we go. So I would encourage you to pause the video and try this one. What you will go ahead and get as your answer is 1/2, but I'll go ahead and post the solution associated with it when I post a complete form of the notes after class. So let's look at a few more examples down here below. This one just seemed a little trivial, so I made it a little bit more interesting by adding some natural logs. That just seemed like a natural thing to do. Natural, anyway. So this one right here is a scenario where you are going to have infinity over infinity, and which is another indeterminate form. So again, this infinity over infinity actually requires some understanding of the function. So just recall what the secant function looks like and what the tangent function looks like. So if we were looking at these two functions, they would have asymptotes at pi over 2. So again, this infinity over infinity shows up whenever you're looking at asymptotes. So for example, if we consider secant I'll do in green, if you just remember, looks something like this. And then tangent, well, the +1 will just shift it up a little bit, but it's still going to have, actually it'll shift it up right to where secant is. So this right here would be where the asymptotes are. So what I've done is looked at secant, which is right there in green. Well, that is going to be infinity because it grows without bound. And the denominator, which is 1 plus tangent, is also infinity. So this is, again, another indeterminate form. And you may be able to do something where, like, write secant as 1 over cosine, and maybe then consider what would happen if you distributed it and canceled. So you could still go ahead and try just algebraic techniques. But this is really going to be nice when you take the derivative because the constant's going to disappear. So let's go ahead and look to take the derivative of the top and bottom separately. So the limit as x approaches pi over 2, which were our original functions had asymptotes. And now let's go ahead and take the derivative of secant, which is secant of x times tangent of x. And now divide this by the derivative of 1 plus tangent, which is just going to be secant squared of x. Notice here that the secants will cancel, or at least one of them will. So we have so I'm not taking another derivative yet, I'm just cleaning up. So I could write this as tangent of x over secant of x. And again, tangent and secant seem much nicer to deal with, namely because there's no constant here. So I'm going to just do one more algebra step, or really this is a trig step, I guess I should say, and rewrite tangent as sine of x over cosine of x. And if you think about secant, remember, secant is 1 over cosine. So what really we're doing is we're dividing by 1 over cosine of x. So the secant in the denominator, I'm just rewriting this horizontally instead of vertically. I'm rewriting secant as 1 over cosine. And notice, again, I'm using division because secant was in the denominator. Multiplying by the reciprocal, notice that our secants will cancel. Or not our secants, our cosines will cancel. So this cancels with this if you were to look at the multiplying by the reciprocal. So all we really have here is, I don't know why I put infinity here. This should be pi over 2. The limit as x approaches pi over 2 is just going to be evaluated in sine, which is going to be the limit, evaluating it at the limit, plug in pi over 2, we get an answer of 1. So whenever you're looking at asymptotes is where you're going to be getting indeterminate forms of the shape infinity over infinity. And these two functions over here the numerator and the denominator look a little bit complicated, I decided to do something a little bit more interesting. Again, notice again, they have the same degree, so you would have an asymptote, you'd have infinity here. They grow at the same rate, but remember the natural log function looks like this. So if you considered 0 from the right-hand side, you would actually have negative infinity over negative infinity, which can indeed also be an indeterminate form. So go ahead and pause the video, try this one out, and I'll walk through the solution in a second. So here's the worked out solution for the one given here. The one thing that you should remember is that you still need to use the chain rule occasionally. So the derivative of this numerator is 1 over whatever's inside, because remember the derivative of ln of x is 1 over x. So that is where this came from. Then the derivative of the inner is where this 2x plus 4. When you take the derivative of ln of x, you get 1 over x here. And just remember that whenever you are dividing, you could also think about it as multiplying by the reciprocal. This step, what happened is the 1/2, you could think about an x came out in front, so it canceled with that one. And then, of course, plugging in the limit, you get 0 over 0 here. So you get 0 plus 4 to get 4, and 0 plus 4 to also get 4, which 4 over 4 is 1. So this illustrates a trig example where you have infinity over infinity, a logarithmic example where you have infinity over infinity. And let's go ahead and look at one more example before we end the recording for today. And let's go ahead and look at this one on the right. I would encourage you to try this one on the left. The one on the left, the answer will be 0, and I will go ahead and post the answers, the work steps for that. But again, one thing I want to caution you about when it comes to this one on the right, when you use Hôpital's rule. So let's go through the steps. Again, remember that e to the x just looks like this. And of course, if you were to consider what is happening as it goes to the right, it grows without bound, and a parabola looks like this. And as you go to the right, it is again growing without bound. So you have infinity over infinity. So that means I could go ahead and take the derivative of the top and the bottom separately. So the derivative of e to the x is e to the x. Derivative of x squared is 2x. Just like above, you get infinity over infinity. Do one more step or one more application of Hôpital's rule. Well, again, you get e to the x, but this time over 2. Remember, the limit as x goes to infinity of a constant, the limit of the constant is the constant. So in this case, it's going to be infinity over 2. Think about what is this? This is, we're saying the top function grows without bound. The bottom will be a constant, so it will be 2. So this is not indeterminate. This is where the limit is actually infinite. So again, remember the indeterminate form is infinity over infinity. Infinity over a constant, well, that's just telling us the behavior of the function. That is to say the actual limit would be infinity or the limit does not exist. So there are a few other things that we will want to go ahead and just look at to make sure you're comfortable with dealing with. And if you notice down here below, these functions are not written as fractions. So we have to actually do a little bit of work to go ahead and get this into a form where we can use Hôpital's rule. So we'll illustrate that in the next video. Go ahead and start practicing this. And if you have any questions, let me know. And again, we only have about 2 weeks left in the semester, so finish the semester strong. And as always, feel free to contact me if you have any questions.